This presentation introduces recurrent neural networks, RNNs, and gated recurrent units, GRUs, essential in processing sequential data. Recurrent neural networks, RNNs, are a type of neural network designed to process sequential data, such as text, speech, or time series. Unlike regular neural networks, RNNs work step by step, using the hidden state to remember past inputs and maintain context. This ability to retain memory makes them ideal for tasks like autocomplete, speech recognition, language translation, and sentiment analysis. Essentially, RNNs excel at understanding patterns and relationships within sequences, enabling them to perform tasks that require context and continuity. The schematic diagram of a recurrent neural network, RNN, illustrates how information flows over time in a sequence. Each time step T involves an input, XT, and a hidden state, HT, which represents the memory of the network. The hidden state is computed using the previous hidden state, HT1, the current input, XT, and a mathematical equation that applies weights, WH, WX, and a bias, BH. The activation function, typically 10, introduces nonlinearity to the process. The unfolding in the diagram shows how RNN processes sequences one step at a time, maintaining a connection between past and present through the hidden states. This makes RNN ideal for tasks requiring context, like language modeling or time series analysis. This slide demonstrates how an RNN processes information step by step to calculate the hidden state, which is essentially the memory of the network at a specific time. Inputs. We start with some assumed values for the current input, the previous memory, hidden state, weights, and a bias. Step-by-step process. First, the RNN combines the influence of the previous memory and the current input using weights. Then, it adds a small adjustment called bias to fine-tune the result. Finally, it applies a mathematical function to make the result more consistent and manageable. Outcome. After these steps, the RNN produces a new hidden state, which reflects the combined effect of past and present inputs. In this example, the result is approximately 0.964. This slide shows how an RNN can be used for named entity recognition, NER, a task in natural language processing, NLP, where entities like people, organizations, and locations are identified in a sentence. Example sentence: Kelly worked at Google in San Francisco. The model identifies Kelly as a person, Google as an organization, San Francisco as a location. How it works. Each word in the sentence is fed into the RNN one at a time. The RNN processes each word while remembering the context from previous words through its hidden state. At each step, the RNN outputs the corresponding entity label, e.g., person for Kelly, organization for Google. The RNN uses its sequential processing ability to understand relationships and context in the sentence, enabling it to correctly label each word as a specific type of entity. This slide explains why gated recurrent units, GRUs, are often preferred over recurrent neural networks, RNNs, using the example of predicting customer behavior. In scenarios where a company needs to predict if a customer will make a purchase based on past interactions, RNNs struggle with long-term memory due to the vanishing gradient problem. This means important information, like a product viewed a week ago, is often forgotten by the RNN. GRUs solve this issue by using update and reset gates, which help retain relevant information and discard unnecessary data. For example, if a customer clicked Add to Cart earlier, GRUs prioritize this critical information even after processing a long sequence of interactions, improving predictions. This slide introduces the Gated Recurrent Unit, GRU, which is a type of recurrent neural network, RNN, designed to handle long-term dependencies more efficiently. GRUs achieve this by using two key mechanisms: update gates and reset gates. These gates control what information is kept from past inputs and what is forgotten, ensuring the network retains only the most relevant details. This makes GRUs highly effective in tasks like speech processing, machine translation, and time series analysis, where remembering important past information is crucial for accurate predictions. GRUs are preferred in many cases because they simplify the process while being computationally efficient. This diagram illustrates how a gated recurrent unit, GRU, processes information at a specific time step. GRU uses two key mechanisms: the reset gate and the update gate. The reset gate controls how much of the past hidden state, T1, is forgotten, allowing the model to focus on relevant new information from the current input, T. The update gate determines how much of the new information is added to the current state and how much of the past state is retained. Together, these gates compute a candidate hidden state, T, and then combine it with the past state to produce the final hidden state, T. This efficient gating mechanism allows GRUs to capture long-term dependencies while avoiding the vanishing gradient problem, making them effective for tasks involving sequential data like time series analysis or speech processing. This slide builds on the previous explanation of GRU and focuses specifically on the reset gate, an essential component of the GRU architecture. The reset gate determines how much of the past information, T1, should be forgotten when calculating the candidate hidden state for the current step. The gate uses a sigmoid function, sigma, to weigh the influence of the current input, T, and the previous hidden state, T1. This mechanism allows GRU to selectively discard irrelevant past information and focus on the current context. For example, in the given scenario, the reset gate helps decide whether to retain or forget specific details, such as dumplings for Wang's preferences, indicating Chinese cuisine, versus sushi and ramen for Chen, indicating Japanese cuisine. The selective memory update ensures that only the most relevant information contributes to the decision-making process, making GRUs more efficient at handling complex sequential data. This slide continues from the previous one and highlights the update gate, another crucial component of the GRU. While the reset gate determines what past information to forget, the update gate decides how much of the past hidden state, T1, should be retained and how much new information from the current input, T, should be added. Using the sigmoid function, the update gate generates a value, T, between 0 and 1 to weigh the importance of past and current inputs. For example, in the scenario of Wang and Chen, the update gate ensures that relevant memories, such as Chen's preference for sushi, are retained. This ability allows GRUs to prioritize critical details over a sequence, ensuring the model focuses on essential information while efficiently managing memory updates. Together, the reset and update gates make GRUs highly effective for sequential tasks, as they can selectively forget irrelevant details and retain what matters most. This slide provides an example of how GRUs solve real-world problems, such as predicting a customer's favorite cuisine or purchase behavior. The challenge with RNNs is that they struggle to retain critical early information in long sequences due to the vanishing gradient problem. For instance, if a customer viewed a product a week ago, this key interaction might be forgotten by the RNN, impacting the prediction accuracy. GRUs address this issue using update and reset gates. These gates help retain relevant early interactions and discard unnecessary ones. For example, if a customer added a product to their cart earlier, the GRU prioritizes this memory while processing new interactions, ensuring it contributes to the final decision. This capability makes GRUs efficient and accurate for tasks involving sequential data and long-term dependencies. This slide explains the reset gate in a GRU, which decides how much of the previous hidden state should influence the current step. 1. Step-by-step process. The reset gate takes the current input, 2, and the previous hidden state, 0.5. Using weights and a bias, it calculates how much of the past hidden state should be retained. The result is passed through a sigmoid function to scale the value between 0 and 1. In this case, the reset gate's value is approximately 0.777. This means about 77.7% of the past information is considered relevant and will be used in further calculations. The reset gate helps the GRU focus on important past details while ignoring irrelevant information. This slide explains how the update gate in a GRU works, which controls the balance between retaining past information and incorporating new information. 1. Step-by-step process. The update gate receives input from the current value, 2, and the previous hidden state, 0.5. Using predefined weights and a small bias, the GRU calculates the weighted influence of both the past and the current input. The result is passed through a smoothing function, sigmoid, which outputs a value between 0 and 1. In this case, the update gate's value is approximately 0.777. This means about 77.7% of the past information will be retained, and the remaining will allow new input to influence the final state. This dynamic adjustment enables the GRU to focus on relevant past details while adapting to new data. This slide explains the process of calculating the candidate hidden state in a GRU. The candidate hidden state combines the current input and relevant information from the past, adjusted by the reset gate. 1. Step-by-step process. First, the reset gate modifies the influence of the past hidden state. In this case, about 77.7% of the past information is considered, resulting in a value of 0.388. Next, the GRU combines the contribution from the current input and the adjusted past information, adding a small bias for fine-tuning. Finally, the sum passes through a smoothing function, producing a candidate hidden state value of approximately 0.839. The candidate hidden state is an intermediary result that ensures only the relevant portions of the past and current inputs are carried forward, making the GRU efficient and effective for sequential tasks. This slide demonstrates the calculation of the final hidden state in a GRU, which is a combination of the candidate hidden state and the past hidden state, controlled by the update gate. 1. Step-by-step process. First, the update gate determines how much of the past hidden state should be retained. In this example, about 22.3% of the past hidden state is kept. Next, the update gate also controls how much of the candidate hidden state, calculated earlier, should contribute to the final hidden state. Here, 77.7% of the candidate hidden state is used. Finally, these two components are added together to produce the final hidden state. In this case, the result is approximately 0.763. 2. Key insight. The final hidden state effectively balances old and new information, ensuring the GRU retains essential past details while incorporating relevant new data. This mechanism allows GRUs to handle sequential data with high accuracy and efficiency. This slide introduces the concept of sentiment analysis, a natural language processing (NLP) technique used to identify the emotional tone of a given text. It categorizes text into three main types: positive, negative, or sometimes neutral sentiment. Categories of sentiment: bullet, positive sentiment, indicates favorable opinions or emotions. Example: I love this product, is classified as positive. Bullet, negative sentiment, reflects dissatisfaction or unfavorable opinions. Example: this is terrible, is classified as negative. Bullet neutral sentiment represents neutral or mixed emotions, often used for balanced statements. Example, "It's okay" is categorized as neutral, although this category may not always be used depending on the task. Sentiment analysis is widely used in applications like customer feedback analysis, social media monitoring, and market research to understand public opinion.